So the binomial coefficient, which is what you see here, is something that comes up very often in the discussion of a binomial series. And you can pronounce this or read it out like k choose n. And so there are a couple forms you might see it in. You might see it like this, or you might see it expanded like this. So how would you go from this first form to the second form? How do you think these two things are equivalent? So let's take a look. So the first form says it's k factorial divided by n factorial k minus n factorial. So what do we know about factorials? Well, if we have, let's say in general, a factorial, we're just going to keep multiplying successive terms that have a difference of 1 from each other. So we're going to end up doing a, then we're going to subtract 1, a minus 1, then we're going to subtract 1 again, a minus 2, then we're going to subtract 1 again, a minus 3, and etc. And it's just going to keep going on forever. For example, if we had 3 factorial, it's going to look like 3 times 3 minus 1 times 3 minus 2, which is going to look like 3 times 2 times 1. So how do you think we can expand or I guess kind of break down the numerator of the first expression on the left? So the first thing we can do is expand the factorial. So it's going to look like k times k minus 1 times k minus 2 times k minus 3. That's going to keep going on and on and on. And then let's pick some arbitrary point to resume our factorial. So let's pick k minus n plus 2. And then if we take away 1 from that, we're going to have k minus n plus 2 minus 1. So if we're taking away 1 from this, we're going to just have plus 1. Then if we take away 1 from this to get to the next term, we're going to have k minus n. And then this is going to keep going on forever. It doesn't end here. So really right here, what we have is k minus n factorial. For example, I could write 3 factorial as 3 times 2 factorial. So that's all we've really done here is we've used that property to realize that this is just k minus n factorial because it's going to keep going on and continue multiplying successive terms. And then we can put that denominator back, which is n factorial k minus n factorial. So now you might notice that the k minus n factorial cancels off. And what we're left with is the expression that you have here, which is k times k minus 1, k minus 2, dot, 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 all the way until k minus n plus 1. So this just kind of collapsed back into the dot, dot, dot there. And divided by n factorial. So that's the expanded expression that you see right here. So one of the misleading things you might want to believe looking at this expression is that you always have this kind of k factorial in the numerator when you expand this coefficient, but that's not necessarily the case. So let's look at a few expansions to see what I mean. So it's always true, just as a rule, that k choose 0 is equal to 1, no matter what. So in this expression here, let's set up a table. So this can be our kind of binomial coefficient. This can be the value, and this can be the number of factors from k factorial. So the first one, we have k choose 0. The value is always 1, and we have no factors from k factorial in this expression. Then what if we do k choose 1? Well, now what this is going to look like is k over n factorial, which is going to be equal to k over 1 factorial, because our n value here is 1, which is going to be equal to k. So here we have 1 factor from k. And then what if we did k choose 2? So now we're going to have k times k minus 1 divided by n factorial, which is going to equal k times k minus 1 over 2 factorial. So now we have two factors from that k factorial expression. We have the k and we have the k minus 1. What if we did k choose 3? Well, now we're going to have k times k minus 1 times k minus 2 over n factorial, which is going to equal k times k minus 1 times k minus 2 divided by 3 factorial. And now you have 3 terms or factors from the k factorial expression. So really, as n increases, n goes from 0 to 1 to 2 to 3. And as n increases, you gain more terms from that factorial expression. So it's really dependent on the n value in the binomial coefficient. So it's important to look at that and make sure you don't get misled to believing that you always have every single term from k factorial, because that is not the case.